Sample 1 is called Rubion. It's an atmospheric sample that we picked up from a place called Polygon Valley in the crater floor. Rubion is our one and only atmospheric sample. So in this case, the rock itself was old and altered, and it kind of crumbled as we were picking up the sample. And so when things don't go according to plan, we improvise, and we try to still get good science out of it. So in this case, now we have a capture of just the air that was around there, and that's also a valuable sample that we didn't have before. Learning about the atmosphere is important because that tells us what the elements and chemicals are that are in the air on Mars, which is really different than Earth, and it's different than Mars was in the past. And so we can do the same sorts of analyses that you could do on rocks to understand what makes up the air. What makes these two planets so similar but so different? The rocks are one part of the story, the air around the rocks is another part of the story. We decided to drop Rubion in our backup sample depot at Three Forks. There are not many ways to capture air from another planet, and we've got that.
Sample number 2 is named Montagnier. Sample number 3 is called Montagnac. This was our first pair of rock core samples collected from the Artuby Ridge region. We didn't anticipate finding igneous rocks on the crater floor. We thought we might be seeing things like lake sediments and sedimentary rocks for the most part. But instead, what we found were a lot of igneous rocks of a couple of different types. We found that in this rock were sort of pits and cavities and minerals that led us to believe that this rock had encountered quite a large amount of aqueous alteration, so interaction with groundwater, sometime after it was deposited. We're really excited about igneous rocks because once we have those rocks in laboratories here on Earth, we can use all sorts of laboratory techniques to understand the crystallization age. So it helps us get a very exact age for when these rocks were forming, which is a really useful thing that we've never been able to do before on Mars. Montagnac was drilled and sealed in the same sol, and the sample is slightly larger, so that is the sample that we kept on board the rover, whereas we placed the Montagnier sample in our Three Forks sample depot. To celebrate the collection of our first sample pair on the surface of Mars, we used the camera on the end of our robotic arm called Watson, and we took a celebration selfie.
Sample 4 is called Salette, and sample 5 is Coulette. We picked these both up in a region called South Zeta in the crater floor. These samples were interesting because they captured some of the diversity in terms of minerals that are in the rocks in the crater floor. So we saw signs that we think are from sulfates. We saw these little white crystals, and we think those are captured in the rocks that we collected. And those are evidence of alteration with water of the rocks that are on Mars. We also saw really strong signals of carbonates. And carbonates are exciting because they are also a record of water interaction with rocks and indications of pH neutral environments, which means that the environment was likely habitable a long time ago. We also saw signs of hydration, which means there's actually water trapped in these rocks. Out of these two samples, we decided to drop Coulette in our sample depot at Three Forks. Sulfates and carbonates and phosphates tell us more about the aqueous history of Mars, and so we were able to pick up that evidence in these samples. Sample 6 is called Robine, and sample 7 is Malay, and we got them from a rock called Isol in South Zeta in the crater floor. In order to learn more about a rock to decide if we actually want to pick up a sample there, we do what's called an abrasion patch. So we take a bit on our rover and we scrape off the surface of a rock, and so you can see some of the interior that's less altered by the exterior environment. In the abrasion patch associated with these cores, we saw this beautiful big sulfate crystal that looks exactly like a polar bear. And I remember it so strongly because we saw signals that look like sulfate, we saw signals that look like hydration, and it had another chemical that we think is either perchlorate or phosphate. These samples are interesting because they capture some of the diversity of minerals that we saw in the crater floor. And we saw things like white sulfate crystals. Those are exciting because on Earth, they can preserve signs of life for a really, really long time. For me as an astrobiologist, the other really exciting thing about this rock is that we saw multiple types of signals that are consistent with organics. And organics are the building blocks of life, and they're also signs of potential habitability in this environment. So maybe there are organics in the sulfate crystal that's in that polar bear in this rock. Out of this pair, we dropped Malay in the sample depot at Three Forks. That mix all together in just one 100 micron spot, which is a really, really small area. That was really unique and exciting about this rock.
Sample number 8 is called Hahoni. Sample number 9 is Atsa. This was a sample pair collected near our Octavia E. Butler landing site. This particular outcrop was interesting because we think it was slightly less altered and represents likely the most pristine of the igneous rocks that we've collected. Pristine refers to how fresh of a surface it is, essentially. And so some of the other rocks that we collected have evidence for interaction with groundwater. There's minerals in the rocks that form in the presence of water, like carbonates and sulfates and things like that. We didn't see that same type of evidence at this particular outcrop near our landing site, and so we think this pair of samples encountered less interaction with liquid water than some of the other samples that we collected. There were a couple of sols in between drilling and sealing for Otsa, so we dropped the Otsa sample in our Three Forks sample depot. This sample pair is from the Maz Formation. So we collected a couple of pairs from the Seta Formation. We collected one from the Maz Formation. And then as we were finishing up our crater floor campaign, we wanted to collect one more sample pair to represent the Maz Formation. So we have roughly the same number of samples from each of the igneous formations that we've encountered. And so this was a very valuable sample pair to collect.
Sample 10 is called Swift Run, and sample 11 is Skyland, and we got them from a rock called Skinner Ridge in the Delta Front. These samples are really interesting because they're the first ones from the Delta Front. So we're out of the crater floor, we're into the Delta Front, and what made this rock particularly interesting is carbonate was everywhere. This was like a carbonate rock. And so in a lot of the other rocks we looked at previously, there was variation across even a small area. There were all of these different minerals sort of clustered together. In this rock, you could see that there was textural variation, so you could see different grains, but this carbonate signal was really, really strong. And carbonate is that mineral that shows evidence of water alteration of rocks, especially in a possibly habitable environment. Out of this pair, we dropped Skyland at our Three Forks sample depot. Deltas on Earth are really good places for habitability and astrobiology studies because they can preserve signs of life for a really long time, and they're usually hotbeds of life activity. And carbonate minerals, which is something that we saw really strongly in these samples, they can preserve organics and signs of life for a very long time.